Hello, in this video we're going to cover ionic bonding. So this is one type of bonding that occurs in chemistry. Now there are two main types of bonding in chemistry. There's ionic bonding, where atoms will lose or gain electrons to form bonds. So here we have the example of lithium, and it's giving one of its electrons to fluorine. So lithium will lose an electron, fluorine will gain an electron, and they'll end up forming an ionic bond with each other. The other type of bonding is called covalent bonding, and this is where atoms will share electrons to form a bond. So for example, previously we said that hydrogen is one of the elements that likes to form a diatomic molecule. So it's not very stable as a single atom. It wants to share its electron with another hydrogen atom to form H2, a diatomic molecule. But we'll talk about covalent bonding in chapter 4, the next chapter. So this chapter is focusing on ionic bonds and ionic compounds. Now, why do atoms transfer electrons between each other? This has to do with something called the octet rule. So chemical bonds are formed when electrons in different atoms interact with each other to make an arrangement that is more stable than when those atoms were apart. So for example, lithium and fluorine might not be very stable when they're apart, or on their own, but they're going to be more stable together if lithium gives an electron to fluorine. So chemists have concluded that atoms are especially stable if they have 8 electrons in their outermost shell. So this is called the octet rule. So for example, last chapter we talked about the noble gases in group 8, and we said that the noble gases are very unreactive because they're very stable on their own. So this is because each of the noble gases have 8 valence electrons, except for helium, which has only 2 electrons total, right? But the noble gases are really stable because they're completely filling an energy shell. For example, neon completely fills in level 1 and level 2. Argon completely fills in level 1, 2, and 3. Krypton 1 through 4. So these are just very stable elements, and all of the other elements want to be stable, like the noble gases. So all of the other elements want to have 8 valence electrons. So how can atoms achieve 8 valence electrons? Well, it depends. Some atoms are going to lose electrons, some atoms are going to gain electrons in order to achieve 8 valence electrons. Now, when that happens, when atoms lose or gain electrons, they're no longer electrically neutral like we've been assuming this entire time. They are going to have a charge, either positive or negative. And these charged particles are called ions. So, for example, let's look at sodium. I mentioned before, sodium is very reactive. It's one of the alkali metals, and if you were to drop sodium in some water, it would cause an explosion or a spark. Sodium's very reactive. And part of the reason for that is it's not very stable. It wants to react. It has 1 valence electron that it kind of wants to give up, right? So let's look at this figure showing sodium. So remember, sodium is number 11 on the periodic table. So it has 11 protons, and when it's electrically neutral, it has 11 electrons. So 11 protons, 11 electrons. So that means we have 11 positives and 11 negatives, right? Protons are positive, electrons are negative. So the charges cancel each other out and we have an overall zero charge. So sodium is neutral. However, if sodium gives up its one valence electron, then it's actually going to have 8 valence electrons. So that's shown over here on the right. So remember, sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Now, if it loses its one valence electron, then its highest energy electrons will be in energy level 2. And there's going to be 8 electrons in energy level 2. So we can see that in the figure. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons in energy level 2. So that's what sodium wants. It wants to just have those 8 level 2 electrons so that it'll be more like a noble gas. So once that valence electron goes away, then sodium will have 11 protons still, because remember, the number of protons defines the element. So we'll have 11 positives, but now we have one less electron, right? So we have 10 electrons or 10 negatives. So these are not going to perfectly balance. We have one extra positive in our atom. So that means we're going to have an overall charge of +1. So now this is the sodium ion. Now the sodium ion is super stable because again, it has those 8 valence electrons, just like a noble gas. And that's a good thing because our bodies need sodium ions to survive. But obviously we don't want pure sodium. Pure sodium is very reactive. We want the stable version of sodium, the sodium ion. Now, there is a term that might come up in your readings, and that term is isoelectronic. So isoelectronic refers to an atom and an ion of a different atom, or two different ions, that have the same electron configuration. So again, we said that sodium, when it's electrically neutral, has an electron configuration of 1s2, 2s2, 2p6, 3s1. Now, when we gave up that 3s1 electron, sodium had a new electron configuration. Or I should say the sodium ion has a new electron configuration. So its electron configuration is 1s2, 2s2, 2p6. And this is exactly the same as neon's electron configuration. And remember, neon is a noble gas and is super stable. So this just further confirms that the sodium ion is going to be really stable because it has the same electron configuration as a noble gas. So we would say that the sodium ion is isoelectronic with the neon atom. All right, so let's do a practice problem. What is the electron configuration of magnesium? And we actually already did this, right? We talked about magnesium when we did the noble gas configurations, or the abbreviated configurations. So once you figure out what the electron configuration of magnesium is, try to see if you can figure out how many electrons magnesium would need to gain or lose to achieve an octet. And then which noble gas would be isoelectronic with the magnesium ion? So I'll let you work on this on your own first, so feel free to pause the video, and when you unpause, we'll go over it together. Okay, so let's write the electron configuration for magnesium, and we'll write the full configuration so we can see everything that's happening, right? So magnesium has an atomic number of 12. So that means magnesium has 12 protons, and if it's electrically neutral, it has 12 electrons. So the electron configuration is 1s2, 2s2, 2p6, so that's 10 electrons, right? And we need two more, so those will go into 3s. So we have 3s2 at the end. Okay, so how many electrons would magnesium need to gain or lose to achieve an octet? Now, typically, we're going to gain or lose valence electrons. So if we look at magnesium's electron configuration, its valence electrons are in the highest energy level, which is 3 in this case. So magnesium has 2 valence electrons, and it wants to have 8. So we have two possibilities. Magnesium could either gain 6 more electrons, or it could just lose 2 electrons, right? So which one do you think would be easier, to gain 6 electrons or to lose 2 electrons? Losing 2 electrons would be much easier, right? So magnesium is going to lose 2 electrons. Okay, so once it loses the 3s2 electrons, its new electron configuration will be 1s2, 2s2, 2p6. Now, which noble gas is isoelectronic with the magnesium ion? So which noble gas has that same electron configuration in number 2? Neon, right? We just looked at that with sodium. So neon is isoelectronic with the magnesium ion. Now, one other question that I should have put on here, what is the charge on a magnesium ion? So originally, we had 12 positives and 12 negatives. But once magnesium loses its 2 valence electrons, it still has 12 positives, or 12 protons, but now it only has 10 negatives, or 10 electrons. So what would its charge be? 2 plus, right? Because we have 2 extra positives, or 2 extra protons, compared to the number of electrons. So we can actually write this as magnesium 2 plus, or plus 2. Either one is fine. Okay. Now, I mentioned that some atoms can also gain electrons to obtain an octet. So chlorine is one of those atoms, so let's look at that a little bit more closely. So chlorine has an atomic number of 17. So it has 17 protons, so 17 positives, and when it's electrically neutral, it has 17 electrons, or 17 negatives. So that means it has a 0 overall charge, right? The positives balance the negatives. Now, we also know that chlorine is in group 7 on the periodic table. So that means it has 7 valence electrons. We can also see that in its electron configuration up above, its highest energy electrons are in level 3, and if we add those superscripts together, 2 plus 5 tells us that we have 7 valence electrons. So it would be super easy for chlorine to just gain one more electron and have an octet, right? And that's exactly what happens. Chlorine can gain an electron from another atom, and its electron configuration, instead of the end being 3s2, 3p5, it's now going to be 3s2, 3p6 because we gained an electron. So again, just imagine an electron from another atom coming in and adding to chlorine. So chlorine now has 17 protons and 18 electrons. So instead of having extra positives, chlorine has an extra negative. So its charge is now 1 minus. So this would be the chloride ion. And we'll talk about the naming a little bit later. Now we talked about isoelectronic species, right? So now that chlorine has that extra electron, it is isoelectronic with the noble gas argon. So argon also ends in 3s2, 3p6. And notice that chlorine now has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So now it is super stable, and that is a good thing because, for example, table salt has sodium ions and chloride ions in it, and we want to have stable ions in our food, right? We don't want anything to react. So let's look at some trends here with the ions that we've talked about. So in many cases, elements that belong to the same group or column on the periodic table form ions with the same charge. And that's because they have the same number of valence electrons. So remember, we said that everything in column 1 has 1 valence electron. Everything in column 2 has 2 valence electrons, and so on and so forth, right? So notice that on the left-hand side, everything in column 1 has a +1 charge. Everything in column 2 has a 2 plus charge, or +2 charge. They're the same thing. And then in column 3, we have just aluminum. You don't have to worry about anything else in column 3. But that has a 3 plus charge. So those elements in columns 1 through 3 are all metals. And notice that they all have positive charges. So that means that they all lost electrons. So we could write here at the top, metals lose electrons to gain an octet. Now, on the other hand, if we jump over to column 5, we're going to skip column 4 because column 4 elements tend to form covalent bonds instead of ionic bonds. So we'll get to that in chapter 4. But let's skip over to column 5. We know that everything in that column has 5 valence electrons. So would it be easier for those elements to lose 5 electrons or just gain 3 electrons to get to 8 electrons? Well, it would be easier just to gain 3 electrons rather than lose 5, right? So everything in column 5 is going to gain 3 electrons to have an octet like a noble gas, which means that they'll have a -3 charge. Now everything in column 6 has 6 valence electrons, and so it's much easier for them to just gain 2 electrons to have an octet. So everything in column 6 will gain 2 electrons and become a -2 ion. And then everything in column 7, just like chlorine, has 7 valence electrons, so it's really easy for each of them to gain 1 electron and become a -1 ion. Now we're not going to talk about column 8 because they're already stable. They already all have 8 valence electrons, except for helium, which only has 2, right? So notice that aluminum lost 3 electrons to become like a noble gas. Everything in column 2 lost 2 electrons, and then everything in column 1 just lost 1 electron. Column 5 elements gained 3 electrons to become like a noble gas. Everything in column 2 gained 2 electrons. Everything in column 6. Everything in column 7 gained 1 electron to become like a noble gas. Also notice that in columns 5 through 7, those are nonmetals. So nonmetals gain electrons. So this is why we went over metals versus nonmetals, because this is going to help us determine if something will lose electrons or gain electrons. So again, metals lose electrons, nonmetals gain electrons. And we just have to figure out how many electrons are lost or gained based on which column the element is in. So hopefully that helps a little bit with understanding the trends with ions. It might take a little bit of practice and a little bit of memorization, but we'll definitely get some practice in. So I mentioned we were going to go over the names of ions. So you might have noticed that when we talked about sodium becoming an ion, all I did to name it was I just put ion at the end. So it was the sodium ion. So positively charged ions are called cations. And the way that I remember that is cats are positively charged. So a cute way to remember it, right? Now, negatively charged ions are called anions, and we have to name these in a slightly different way. So we do put ion at the end, but we also replace the end of the element's name with IDE. So you probably noticed that instead of saying the chlorine ion, I called it the chloride ion. So we would do the same thing with other elements. So for example, let's say we have fluorine. So fluorine is similar to chlorine. It has 7 valence electrons. So it wants to gain an electron to become more stable and have a total of 8 in its valence shell. So then that means it would have a 1- charge as an ion. And this would be called the fluoride ion. So instead of the fluorine ion, it's the fluoride ion. So again, with positively charged ions, you just add ion at the end. But with negatively charged ions, we have to replace the end of the name with IDE and then add ion. All right, so anyway, going back to our ionic bonding, let's talk about ionic compounds. So I mentioned that some elements can give up electrons, some can gain electrons. So let's talk in particular about a compound we're all familiar with, table salt. So table salt is composed of sodium ions, so Na+, and chlorine ions, Cl-. So earlier we said that sodium can lose its one valence electron to become more stable. And then chlorine can gain an electron to become more stable. So these two are going to team up, and the sodium atom is going to give its one electron to chlorine, and now they're both stable. They both have 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in their ionic forms. So they end up teaming up together, and we get the compound sodium chloride, which again is just table salt. All right. So I think we'll stop there for now. Next time, we're going to talk about Lewis diagrams. So Lewis diagrams are going to help us better visualize how many valence electrons atoms have. And that can help us determine how many electrons something can give up or something can gain. So I will see you then.